sparsity. Okay. So sparsity, as you see here, is going to become a keyword that actually describes many different things with something in common, with some similar flavor in common. Okay. And what I want to do today is basically start by trying to connect sparsity with what we have seen so far, and so I'm going to put myself in a slightly simplified situation, and then we're going to go back and take a general point of view. Okay. So the way I want to start the problem is by considering that, if you have data, and if you decide to stick to linear models, or if you want the linear kernels will disappear from now on for a few lectures, so we can just think about linear functions. Okay. If you want to think about this, essentially behind the estimation problem, the learning problem, there is actually an inverse problem. Okay? An inverse problem is essentially a linear inverse problem is a linear system. Okay? Could be maybe this could be an operator, doesn't matter. In the finite dimensional case, it's solving a linear system where the idea is that you know this, and what you're looking for is this. Okay? And so it's an inverse problem because, in some sense, if you could invert, you can view this as something which you observe through this matrix, and then you want to invert the observation process. So the interpretation inverse problem is you have some quantity you want to understand, you measure it, okay? And then once you have measurements, you want to try to go back to the actual observable quantity. Roughly speaking, here you can think that in some sense you have some output you want to observe, okay? And by taking this observation on the input, you are actually making measurements, and then you want to go back to the true model. In this case, the true model is W. In the standard inverse problem setting, typically X, so just forget about the learning setting for a minute. You just have a linear system. If you open the book about this kind of problems, there is tons of stuff, okay? In optimization, in the theory of inverse problems, in linear system theory, numerical linear algebra. If you look at estimation problem like this, typically the setup is that Y is affected by noise. Maybe it's deterministic noise, maybe it's stochastic noise, doesn't really matter. There are a bunch of different models. And the typical scenario is that the matrix X is fixed and known, okay, with no perturbation on it. The learning scenario makes life hard because both Y and X are actually noisy, okay? So this is not the real problem we're looking for. What we want to find is look at this as a proxy for the problem where we have infinite data, okay, infinite X's, and Y is potentially noiseless, okay? So we assume that there is some target function F star, and that's what we're shooting for. So the take-home message here is that we're going to start from this problem, but remember that this is not what we want to solve. It's what we can solve, given data. What we would really like to solve is a kind of idealized version of this, where the Y are noiseless and the X are infinitely many. Okay? Try to describe this idealized problem as an inverse problem. Is outside of this, can be done, but is outside of the scope of our discussion here. Okay? So we can discuss this offline. The take-home message here is only, we're going to start from this linear system, and this is what we can solve. Okay? Now, this problem here is a linear system affected by perturbation, both in the operator, in the matrix, and in the data. And so our main goal is to, from this perspective, to try to find stable solutions. Okay? So rich but stable solution with respect to the perturbation here and here. And this is basically what we've been doing so far. Okay? Let me just go step by step in what we have done and what we're going to try to do. What I want to do is to rewrite the pseudo-inverse of this problem in using the SVD of the matrix X. Okay? And then I want to look at Tikhonov, and then I want to see other way of doing things. Okay? So you should help me out with this. So the first thing I want to do is that I want to define, let me do it here, W dagger, which is just X hat dagger Y hat. Okay? So now suppose that this matrix X as the following singular system. Okay, sigma I are the singular values, ui and vi are the singular vectors. How can I write this? You know? Anybody? Okay, I'll write it. Let me call R the rank, meaning the number of non-zero singular values of this matrix. And then basically what you have to do is that you have to take Y, apply UI, you get a number. This is the component of the vector VI, okay? And then here I still have to write 1 over sigma I, which is the singular values, okay? This is just expression of X dagger on the singular system of, X hat dagger on the singular system of X hat, okay? And you see here that the problem is that here both UI, VI, and Y hat, in fact everything, if you change the data, will change, okay? If you change X, everything here will change. And the worry is that because there is a sigma I here, if the sigma I are small, and now you're making changes, okay? Small changes in correspondence to small eigenvalues can have a huge effect. So you can get W's here that are completely different, okay? Yeah.
Sorry, what's the relationship between X hat and X hat dagger?
So X hat, so is this one. Okay, so this is one answer, but let me give you a slightly less annoying one. So X hat is this thing here, right? This is just a singular system. And if I want to write it in some like fashion, this is how, let me apply it to a vector A, okay? Then this would be what? Can you help me with this one? If I want to apply now X to a vector A and I want to write it in this form, okay? So how shall I write it? I have V acting on A, okay? So this is just going to be a bunch of inner products. So I get A VI, okay? Then I get UI sigma I, okay? So this is X. I just rewrote the SVD. And when I take X dagger is the, so say if X is invertible, this is just the inverse. If it's not invertible, it's the inverse up to the first non-zero eigenvalue. And then I chop off the rest because I just put the rank here, okay? And these are the two ways of writing it, okay? Everybody's happy with this? So the point I want to make now is that from this perspective, while this is a perfectly fine solution in the sense that it is well defined and you can compute it, in general it might be unstable when you change the data, okay? And this might lead to lack of generalization properties. If I give you new data, I get a completely different solution, and this is somewhat a signature of when you won't be able to generalize. So what do we do? What have we done so far? Well, in the case of least squares, okay, so it can be shown that this is essentially related to the minimum of the least square problem. Okay? So what do we have done to cure this? So this problem essentially gives you this solution, and this solution has this instability. How did we stabilize the problem? Well, we consider instead of this, it's regularized version, right? And in particular, one way to do it was to add here lambda W square. This is just now Tikhonov regularization. And what do you get here? You get the W hat lambda. How do you write this? Here, somebody, please. Well, you have to take the derivative of that, set it equal to 0, and what you get here is x hat transpose. I don't put the 1 over n here just for simplicity, okay? Plus lambda I to the minus 1 x transpose y. Can you help me out in writing it in this form now? If you remember, I give you kind of a nice rule, which is whenever you have a function like this, you should really think of this action on the eigenvalues, okay? And so you can actually rewrite this by noting that what you're doing is that you're taking y, let it again be hit by ui and by vi, but then you have this operation on the eigenvalues, okay? So what you have is that this part here, remember that if this is the singular value of this, means that sigma square is an eigenvalue of this. So this operation is going to give you this 1 over sigma square plus lambda, but you still have this x transpose, and x transpose and x have the same eigenvalues, okay? And here you get sigma I, okay? So I'm going to be quick because we've seen it in a couple of times. Okay? So as I wrote here x, you could write here x transpose. You will see essentially that the role of v and u swap, but it's the same expression. Okay? All right, so this is the basic expression of Tikhonov in components. And what we discussed the other time is that once you look at this, you could, if you want, consider kind of a filtering perspective, where here you put, say, the components of this vector, okay? And see, here I have sigma i's, and sigma i's, goes from big to small. The eigenvalues here are, or the singular values are positive, okay? And they can be ordered in a non-increasing fashion. And what we want to do here is to put the component that correspond to big eigenvalues first, and then the rest. And then what you see here is basically that your idea is that if you're choosing lambda and you're imposing this constraint so that if an eigenvalue is very small, essentially lambda is going to dominate. And this is just going to become basically 1 over lambda square. Correct? But if lambda is if lambda is very big, it's going to dominate over the eigenvalue, and this is going to be 1 over lambda square. If lambda is very small, this is going to be equal to what? Sorry, this is a mistake. No, that's correct. Sorry. So if lambda is 0 for a certain sigma I, then you get sigma I divided sigma I, and then you go back to there. Okay? So basically this says that what we're doing is some kind of filtering that says that kind of work a little bit like this. It makes a cut here. Okay? So again, this is big and this is small eigenvalues. So it's not quite a cut. You see, another thing we could do is to say, well, in this expression, instead of r, let me put a number smaller than r. Okay? This would be doing something similar. It would basically say, I'm going to keep everything up to here, and then I throw everything away. This is kind of a smoothed version of that. It's not like you throw something away. It's more that you upweight or leave alone the component that are large, and then you downweight, or you depress through lambda the one that would give you a very big contribution. Okay? So far so good? So this is kind of the filtering perspective on Tikhonov. This is the variational perspective. This is the numerical linear algebra perspective. And this, through this expression, we can give a kind of a filtering perspective. Okay? We want to make a couple of comments before moving on to sparsity. So the first one is, last time we discussed another method which was iterative, so computationally more efficient, to compute something that was doing something similar. It was basically just gradient descent of the empirical risk with lambda equal to 0. And we convince ourselves that in fact it's similar, well, I hope we convince ourselves, that it was similar to this because we can give the following expression. So instead of a lambda, this guy had a parameter t. And he had the following expression. Do you remember? This expression here, which is easy to prove in words, is the iteration that you obtain if you run the gradient descent iteration on the empirical risk without regularization for exactly t steps. Okay? If you run the gradient descent on the non-regularized empirical risk for t steps, this is what you get. But then again, I could ask you to try to write this in components. Okay? And these just become the sum over j from 1 to r of gamma, the sum from, I guess, k from 0 to t minus 1. So let me call this k of 1 minus gamma sigma I square, sigma I y hat ui vi. Okay? So again, this is 1 minus gamma. This is just sigma I square. This contributes a sigma, and there is the expression we want. Okay? And if you remember last time, we discussed a bit that if you now take this t to infinity, this becomes exactly a 1 over sigma square, essentially because this is just a geometric series. And then you can really compare this expression, and convince yourself that t here plays essentially the same role as lambda here. Okay? So notice that this gives us a kind of a filtering perspective. Tikhonov is doing filtering. This one is another form of filtering. The intuitive one is the one where you just chop off all the components after a certain value smaller than r, okay, which would correspond to like a square window here. So all this, if you want, define some kind of windowing, okay? And it's all some form of low-pass filtering, in the sense that if you see the components corresponding to large eigenvalue as low frequencies, and the other way around, then this keeps the low frequencies and cuts the high frequencies. Okay? Does this make sense? Okay? So this is give you a kind of more of a filtering perspective on the way you design certain kind of algorithms. And let's try to write for a second. You see, all these methods share somewhat the same form. And it is basically, let's see if, suppose that I want to try to give you a generic form of methods of like that, okay? Let's say I want to try to generalize this to a generic filter function. So I come to you with a filter function, okay? What is a filter function and how shall I use it to design an algorithm? Does it make sense? Let's try together an expression, okay? Want to write down a generic expression of a w hat, say, theta. Theta is the regularization parameter, can be either lambda or t. And here I want to write down the generic filter expression. How do you think I could write it? You see what I'm asking? In some sense, if you see in each of these methods, I define a window, a way I want to window my components, okay? So suppose that I give you a window. How do you use it to design something like that? Is the question clear? So here the window is this 1 over sigma square plus lambda. Here the window is this thing here. If you do the case where you chop off everything after m, this will be an indicator, okay, which is non-zero, 1 up to a point and then becomes 0. These are all windows, okay? Well, but then I can, if you let me call the window G, then perhaps I can write this. where here, this is some general form of window, okay? This is just one notation that describes all those methods, okay? For any choice of G, I get Tikhonov, I get gradient descent, or I get what you might call the truncated singular value decomposition, or spectral cutoff, the one where you put here M instead of R. Okay, all these methods look like this. What they do is that they decide the way you want to window this eigenvalue to depress the components corresponding to those eigenvalues. And they correspond essentially to some form of window that basically have most of the energy for corresponding to the big eigenvalues. There's not much in corresponding to the small eigenvalues. Does this make sense? Okay. So this is nothing about computations, okay? I'm not suggesting that whenever you have a problem, the way to think about it is to first of all do an eigendecomposition and then start to define windowing. We have seen that, for example, for the gradient descent, it's much better to run an iteration. But this shows you a different way of doing things, okay? And one thing you can think a bit of as an exercise, just to just get a third example that when I have time I do in class, but this year I won't be able to do it, is you can convince yourself that if you take this expression and you put here M, okay, smaller than R, you get another algorithm that corresponds to just a specific choice of this. This is easy to see, it's just the indicator, okay? But if you work a little bit, you can interpret the algorithm as the following. Take the data. For those of you who know what it is, do PCA, project the data, and then on project data, just do least squares with no penalty, no nothing. The algorithm you have depends only on the number of projection, but the number of projection is basically the number of eigenvalues you keep. And so the algorithm where you truncate is equivalent to a PCA and then estimation with no regularization. And if you want, that's because PCA is already regularizing. The projection itself is already regularizing. Okay? So try to do this as a little exercise. And this, if you want, is the last comment I want to make about this, which is I don't think we're going to do it in this course, but I imagine that many of you knows that this, the SVD of this, is essentially what, up to a recentering, is what you call the PCA, the principal component of this data set. And from that perspective, you can see that these methods, all the methods that can be written this way, have an implicit assumption that the PCA basis is good. Not only that, the ordering of the principal component is important. The principal components, that are exactly the ones that correspond to big singular values, are more important than the small principal components. Okay? So that's what we're doing here. That's what ridge regression does. That was this truncated singular decomposition. And that's also, surprisingly, perhaps, is what gradient descent with no constraints and no penalty does too. Okay? Any question about this? So again, where we're at is basically we started from regularization with the penalty, and then we start to massage things around for the square laws when we can use linear algebra to convince ourselves that Tikhonov, ridge regression, but also other methods can be seen from a filtering perspective. And basically, this method said there is a preferred basis. In this case, is the principal component basis. And then I believe that there is an ordering on this basis that matters. And what I do is that I say everything that is related to small eigenvalues, I want to decrease the importance. And everything which is related to big eigenvalues, I want to try to keep. And that's what all these methods are doing. So this is the beginning of a little introduction on sparsity, because now you could complain at least about two things. What could they be? That's good. I'm asking you to complain. They're just.
Zero out some of the bases.
Second?
Zero out some of the bases rather than just filtering. Just select some of the eigenvectors.
Not just based on the ordering.
Ordering.
Yeah. So one thing, if you want, is Well, here we are assuming that in some sense we want to keep all the basis elements, okay? But in some sense, well, one intuition, and maybe we want to think about that for a little bit more, is maybe we want to somewhat select some components. Some components are more important than some others, okay? Here we are doing something like that because that's exactly what this cut is doing, right? It's throwing away all the components that correspond to other eigenvalues. So another way to say the comment is, well, maybe I'm also looking to some other way of select components. What is a situation where you might want to do a different kind of filtering or a different kind of selection?
Some of your less important components could be the ones that actually differentiate between your two classes if you're doing a classification problem.
Right? So what he's saying is, imagine that you're in a situation where what really matters are the components corresponding to the small eigenvalues, for example. Okay, if you're in that case, you're really bad luck. Maybe it's not the smallest, but let's say that the ones that are not the biggest, okay? Even more, let me assume that this the vectors you're looking for, it actually has just maybe a couple of components here, okay? And remember that then, so it should look like this, but then there is a bit of noise, a bit of perturbation, so it will also have, maybe some component somewhere else. So by doing a cut like this, sure, first of all, you have to go all the way down here. So let's say that there are three components, these three, okay? To capture that signal, you have to make this a cut very far away from here. And then what you're getting is all these other spurious components that should be zero, but they're typically not because they're corrupted, because this is just a noisy problem. Okay? So one observation is that if your signal looked like that, this doesn't sound like a great idea. Well, because it was designed on another assumption, right? And the other assumption was that all the stuff was on the big eigenvalues. This is observation one. So the one question to start thinking is, how would you fix this? But let me ask the second question, which is, what is the other restriction that we're doing here? Everything depends on what? Well, everything is conditioned in this reasoning to a choice of a basis, right? Everything depends on the basis. And the basis here is the basis of the principal components. But what if it's the wrong basis? Okay? Suppose, for example, that that this is actually a big matrix, and the columns, the rows are, let's say, patients, and the columns are gene expression data. Okay? This is one classical example. And suppose that these outputs are, say, the stages of a disease, more or less aggressive. Okay? And suppose that what you're shooting for is the idea that only a couple of genes will matter. And everybody else, for this perfect, for the best classification in between these two stages. But everything else will not matter. Okay? Then the idea is that it's not the PCA basis, the right one. It's really the orthonormal, the canonical basis. It's really the components of the vector that matters. Okay? Here, for example, you can assume that if you're lucky, say the first two columns, the first three columns are the one that matter. Everything else doesn't matter. So gene 1, 2, 3 are, is what give you the good classification. And then everything else is useless. So if you could go in and just measure these three genes, you would get a very good classification. That's an assumption. That's a reasonable assumption in some situations, okay? Well, then maybe there is a hope to actually try to do some form of selection, as he was saying, but not in this way, which is basically, this is just selecting PCA, right? So we would like to be able to do something like this without having to, stick to the PCA, but perhaps using some other form of basis or dictionaries to decide what's important and what's not. Okay? So these are the two basic intuitions we want to build upon, and that's what we're going to do next. The first is we don't want to filter like that, and for this reason we're going to stick to the PCA for a second, and then we're going to ask the second question, which is going to lead us to the general sparsity perspective, which is, what if I have another dictionary? I come to you and I say, my function depends on your few components here. Okay? Use this assumption. So first thing first, let's stick to PCA. And let's say if I give you the signal that looks like that, okay, with those three big components, but not associated to the big eigenvalues, how would you like to filter out so that you select the best?
Take a bandpass filter.
Say again?
A bandpass filter kind of function for me. If you know which components.
Yeah, that's very good. Yeah. If you knew which three components, so what he's saying is that if you know the components, what you could do is actually try to do something like this and select just those. But if you know the components, as we will see, you will be already in a very good shape. So the first thing is to try to do something when you don't know the components. And if you had the components, you're back into business, because basically now your problem is just a standard estimation problem, okay? So suppose that you don't know what they are. Yes?
One of the magnitudes of these green things, I mean, you align them in terms of eigenvalues, right?
They are just these components. Okay, sorry, these components. So I have these components here, and I order them according to my eigenvalues. So the
magnitude will represent what?
The size of the coefficients. So you basically view as this as the basis, okay? Then these are just the coefficients on this basis. So if this number is big, yeah. So these are the size of the coefficients corresponding to the ith, which is the jth.
But they might have big.
Some of them are big, some of them are small. Okay. So the order here, I order this, right? And the component 1 is the one corresponding to the biggest eigenvalue, component 2 second biggest eigenvalue, and so on and so forth. And then I have this number, and I order them. Okay.
So just the coefficient values there.
Yeah, these coefficients. Okay. And the question is, okay, if I know that the big ones, okay, if I know that the components here are big if the eigenvalue is big, but when the eigenvalue is small, this number is really small, then I can try to just throw them away, and we're in the first situation. But now we're in the situation where, unfortunately, even when the eigenvalues are relatively small, this number is also big, okay? And so now you really want to keep everything. So this is not just an effect of an amplification due to small eigenvalues. It's really an information that matters. So what would you do?
We can learn this function G.
But yeah, you could try to learn that function G, I guess.
Maybe we can move the border from the left to the right, like trying to classify with m values and then m plus 1, and then find the optimal one.
Yeah, so you can try to be greedy, okay? You can try to see one, then another one, and that's kind of one thing we're going to do. But another thing you could do is what? It's like the Columbus effect. Yeah. You could basically say, well, I want to do a complicated problem, potentially, where I fix the number of non-zero components in my function, okay? I say, let me solve this, but instead of an L2 norm, put something related to the number of components, okay? What I'm shooting for is a graphic answer here, okay? And so basically what I'm saying is, if you could, one thing that would be nice is instead of cut like this, how would you feel like cutting? Horizontally, okay? Instead of doing this, well, what you would like to do is to do something like this, okay? Or even better, like this. And you say, if all the stuff that is big, I keep. All the stuff that is small, I throw away. And this would be a way to somewhat not, try to select the components even if you don't know where they are. Okay? Turns out that this has connection with both the idea of being greedy and both the idea of trying to, control the number of components. And in this basic form, the idea is that instead of doing this, what we could do is put another function here. So this is an operator that eats a vector and return a vector. So it acts component-wise, okay? And it's just a thresholding operator. It basically says, if you give me a number A, and if the number A is in magnitude bigger than a threshold lambda, then I'm going to keep it. Okay? If it's smaller than lambda, I'm just going to throw it away and set it equal to 0. Okay? It makes sense? Another way of doing this is replace h with a slightly, so, and this basically, this guy looks like this, right? Well, let's do the first one first. Another way of doing this is to take this, and again, take an operator here that acts on each component of the vector by basically doing a minus lambda a So what this is doing is kind of a soft, this is called the hard thresholding operator. It's basically saying if it's big, you just let it be. If it's small, you set it equal to 0. Okay? So when you're going inside of here, you're basically saying when I have big coefficients, I keep them bigger with respect to a parameter lambda that now becomes my regularization parameter, is the number of components. And if they're small, I throw them away. This one is kind of a smoothed version and says if the parameter is big enough, I'm going to keep it, but I'm going to decrease it just a little bit, okay? And if it's large enough, but it's negative, I'm going to increase it just a little bit. So if you design that, you're going to get something that looks like this, okay? This is lambda and this is minus lambda. So the interesting bit is that it's relatively easy to prove, and this is one, I think, of the exercise of some other piece set, is that if you consider now the solution corresponding to this choice, both these solutions are implementing a notion of this, okay? They're both saying, oh, everything which is big, I'm going to keep. And then I say, okay, I'm going to keep it, but I'm going to decrease it a little bit, okay? Here I'm putting down all positive, but it could be positive or negative, okay? This one says, I'm going to shrink it a little bit, introduce a little bit of a bias. And what you can prove is that it's really easy to see that this solution, okay, this function here, defined just by plugging this there, is actually, so if you write now v hat lambda equal sum j from 1 to r s lambda ui y hat sigma I vi, okay? Then this is exactly the minimizer of, so this is the arg minimum over all coefficients of x hat w minus y hat plus lambda. But the important bit here is that you have to put this L1 norm. Okay? And the L1 norm here is just the sum of the absolute component of the vector. Okay? So here, this is left as an exercise. Okay? So again, the motivation here is if the basis of principal component is good, but my assumption that everything is on the big eigenvalue is not true, maybe I want to change the way I filter. And one intuition is that something like this should work fine, okay? Because it's basically letting go everything which is big and killing everything else. And it's possible to see that, in fact, this one here, we're going to do this calculation in a bunch of ways, but here I'm just showing it once. Oh, sorry, this doesn't make sense. So here I have to take the so this is almost L1 norm, okay? So I'm going to take the coefficients on W, okay, on this basis here. So the Vj, remember the Vj are the one that matters here, right? So I'm going to use the Vj as my preferred basis, and then I'm just going to put these coefficients. Let's think 1 second about this, okay? If you take here a square, so if you were to add here a square, this would be just what? So this is a vector. Vi is what? Is a basis. Here's the sum of the square of the coefficient, which is exactly the square norm. Wow, you guys are fantastic. Give me a lot of satisfaction here. Okay? And really, the basis you put here doesn't matter, okay? This W here doesn't care about the basis you're taking. It's what is called rotational invariant. You can make any change of basis, and this doesn't really matter. This guy here actually depends on the basis, okay? The fact that we're dropping this W makes a huge difference. It makes, you go from this kind of filtering, that is just a low-pass filtering, to this other kind of filtering, which is a completely different kind of filtering, okay? It just takes the stuff with this big I. And this is just, the spectral version of going from this 2 norm to this 1 norm. So very different. Okay? Yeah.
Should there be a lambda?
Of course. It disappeared in the agitation of the mistake. Okay? So from a filtering perspective, here we want to try to go from this kind of low pass. And notice that this is a linear map. Okay? The way it acts on y, this is just a matrix that acts on y. So this whole thing, and you see it from here, is always a matrix applied to y. So these are linear filtering methods in this sense, or linear regularization methods. If you start to do something like this, you cannot, you see, y here enters inside of the nonlinearity. You cannot just write this as an action of a matrix. It's something like first you make the action of a matrix, but then you have to do some nonlinear thresholding on that. So this is a nonlinear filtering. This one and this one are nonlinear filtering, okay? And there are nonlinear regularization techniques in the sense of the way they act on the vector of outputs. Okay, we're in a relatively good shape because we went from linear filtering, linear regularization to this first example. And you see why sparsity, okay? Look at the action of this. This is creating sparse vectors in a very intuitive sense. If the component is smaller than a threshold, you set it equal to 0. If it's bigger, you let it go. This is never the case here, right? Almost never. If you take any of these methods, typically you get something small. And anyway, what's small is typically the one that corresponds to the small eigenvalues. In the case where you truncate, if you put here the indicator function, you do get 0. But again, with this kind of vertical cut kind of strategy. So if you have just one component here, you have to take everything before you get one. Okay? Because you're always doing this kind of low-pass filtering. Okay? So if our goal was only to derive sparse methods using PCA as a basis, we're good to go. Okay? That was our goal. We wanted to try to achieve something that was able to exploit that kind of situation. That kind of situation can be described as the function I'm looking for has only few components, but they might not be the one associated to the big eigenvalues. This kind of nonlinear filtering does just that. And we can go back and actually see that it's some kind of regularization with the new penalty, which is not L2 norm, but is the L1 norm. Okay? And that's why in my list of wish list, the other thing we wanted to try to discuss is, okay, but what if PCA is not the right basis? Okay, what if you have another basis? In the example I show you there, the basis was just the columns themselves, because each column was a gene, and if a gene is important, I want to select it. If a gene is not important, it's not selective. If I do a PCA, so VI can be written in terms of the columns of the matrix, right? The VI is itself a combination of the columns, but God knows which one, right? Suppose that I tell you that I need only one component here. Okay, only the first column here. You cannot find it through this method that we showed there, because there you first have to write everything on the eigenbasis. And you might need a lot, even if there is just one component in this, you might need all the principal component elements to describe just this one element. Okay? So what we want to do next is generalize everything to the case where you actually have a dictionary. Okay? So this is kind of giving you a connection with what we've been doing so far to what we want to do next. In the case of least squares, where you and PCA, where you can exploit spectral theory. Okay, you can exploit diagonalizing matrices to just have this expression. What we're going to do next is move away from PCA, and we're going to keep the least squares for a while, though it won't matter much. So what we want to do next is somewhat abstract some of the features we discovered. And try to see how we can work with general dictionaries. Okay? So let's just take a step back and look at this expression. So first of all, notice that let's write this expression let's rewrite what is the assumption underlying this expression in a couple of ways. So here I'm taking functions which are just linear, right? So they can be written just like this. Okay, where this is RD. Let's write this in components, okay? How does it look like? This is just sum Wj xj. Okay. So if you want, what you're doing now is that if I have to say, the first example you can think of is the one that says exactly, oh, but these are exactly, as I said, these are exactly the component, the columns of my matrix. Okay, these are exactly, each of these elements is exactly one element of this dictionary here. Okay. So suppose that now I tell you that only some of the features, so only some of the entries corresponding to the columns are important. Then what you would like to do? Well, this expression really depended on having this kind of basis, okay? But the hope is that something like this would be useful, okay? Let's try to think a second why. So we want to get there in 2 steps. So the first idea is, as somebody said, well, I can now write down my least squared problem. And my hope is that there exists a true function, okay, so that the best possible solution to the problem should not have this form, but should actually be some W star with some coefficient W star there. And the idea is that most of these coefficients should be equal to 0. Okay? So what we want to do now is try to add a regularization that somewhat enforce this assumption that only some of the coefficients should be different from 0, and the majority of them should be hopefully 0. So one way to do this is to introduce what is called the zero norm of a vector. The zero norm of a vector is actually not a norm, but it's a functional that, given a vector, returns a number. And this is just the number of j such that wj is different from 0. Okay, so you give me a vector. I go in and count how many entries are different from 0. And then that's the zero norm of the vector. So if the zero norm is 0, it means that the vector is all 0. If the zero norm has some other value, this is exactly the number of components different from 0. Okay? So one idea would be to try to use this as a regularizer. So here, if lambda is big zero norm, minimizing the zero norm matters a lot to us. So if lambda is big, the W we're going to find is going to be like what? It's going to be just full of zeros. Okay? If you now put lambda very small, you ignore the sparsity assumption, and all you care about is fitting your data, and you're just going to get some estimation. Okay? So in principle, this is kind of exactly one way of implementing our hope, which is in this case, in the case where what I know is that the coefficients are exactly with respect to the components, to try to make it so that only some coefficients will survive. Okay? So from a modeling perspective, this seems pretty good. What is the issue here, you think?
Hard optimization problem to solve.
It's a horrible optimization problem to solve. Okay? It's continuous, but it's by no means convex. Okay? So in fact, it can be shown that the problem is not solvable in polynomial time. Essentially, that problem is as hard as the intuitive brute force procedure. So somebody mentioned before that if you would know which are the important columns, you could just take those and solve the problem on those. Okay? So the problem here, if you want, is to find them. So what is the intuitive way of trying to find them? I give you the data. Okay? Suppose you have an infinite computer, and you want to find which columns are the ones that matter the most.
Go through and try each column by itself and see how it does, and then try it.
That one. The pairs, the triplets, and so on and so forth. Okay? That it?
Yeah.
So the brute force approach I take all the single ones, then I take all the pairs, and I take all the triplets, and I try them. Okay? And I solve the problem with those. And clearly this is combinatorially hard, right? Even for moderate size, this becomes extremely hard. And it turns out that this brute force is essentially equivalent. If you could solve this solve approach, you would get a solution to this problem. So this non-convex problem corresponds exactly to this kind of combinatorial problems, trying all possible subsets. The problem of solving this is in fact what is called often best subset selection. Or variable selection. You're trying to find among all the possible columns the one that matter the most. Okay? So while this would be good from a computational perspective, from a modeling perspective, computational perspective, this is not feasible. Okay? So one question is how to find meaningful approximate solution to that problem. So before doing that, let's just do a small parenthesis, which is going to be how you go from I'm going to stick always to this linear case, but I just want to make a small parenthesis that is good enough to consider more general situation. Because I promised you that I wanted to go from SVD to general basis, okay? But up to now, I'm actually giving it to another special basis, this one. But how would you be able to suppose that we have still our infinite computer, so we can solve this. But now I would tell you, oh, sorry, I was kidding. This is not the real good model. Here is the basis where everything is sparse. How would you recycle this framework? Let's say that now you have a basis, which is, I don't know, you have phi1, phi p. Okay? You have p elements of a basis. And I tell you, my function is sparse there. What does it mean? That I can write my function in an expression very similar to this. So help me out. I feel super lonely today. So f star x equal what? Well, I have to write an expansion, a linear expansion, so with some wj, over these bases here. So we've seen this several times. Is this a special case of this? For which choice of the phi j? Just the ej, right? The function that selects the jth component, so the canonical basis. So in this case, even in here, there is basically the component just select the main, they select the jth component, okay, the canonical basis. And this is just the general case. There is some phi j that is good enough, okay? So this is a special case of this. But on the other hand, here, if you want, we are basically just changing the notation, okay? So here, basically, it will be useful to just to simplify and not carry around this phi j. We're going to use this notation and think that if either you're considering the special case where this is just xj, or if you want, you just use this change of notation, okay? Just call is the usual trick that when you have a linear model, okay, on some basis elements, you can just think that you're basically renaming. It's just a linear model, okay? Here, the x is the real x. Here is the same thing, just what you did is that you first map the data through the dictionary, okay? So we've done this several times when we're doing kernels. Here we're doing something different because this actually will depend on the phi j, okay? So this is just a change of notation, but the phi j really matters. You won't be able to do this with kernels, okay? Because as you saw there, and as you see here too, this notion really depends on the basis, okay? If you change basis, you change the norm. It's not the same thing. You can have very small norm on one basis and a huge norm once you make just a small rotation. So of course here the big difficulty is again, and perhaps even worse, how you choose the basis or how you use the feature, how you use the dictionary, okay? Because now everything depends really heavily on that. So the point of this parenthesis is just that while I'm going to keep this notation, everything we say works for a generic finite dictionary, okay? It doesn't have to be a basis. Just have to be a finite dictionary, okay? And in that case, instead of x, you could think of a matrix where you first pre-mapped the point by doing this kind of changing, looking at these two measurements. Does it make sense? I would like to keep this notation from now on. Okay? Okay, so now back to this, where again you can think of this as the coefficients on just the column, the coefficient corresponding to the columns or the coefficient corresponding to a dictionary. And now the main question is, okay, now that I know that this would be a good idea, but I cannot really implement this in practice, how could I try to find an approximation? Okay? And a harder question, and this question has, the answer to this question has been on for quite a while. And then a harder question, which we're not really going to touch upon, is do I have any hope to prove condition under which my approximation is as good as the original problem? Or am I just paying a price and solving a different problem? This is not a question we're going to look at too much. What we're going to ask is, what is the natural way to approximate this? And there are essentially two classes of methods, okay? One is what is called greedy methods. This one we're just going to describe. It's in the notes, but I suggest we just describe it in, well, we actually skip it. Let's do this, okay? And if we have time, we're just going to describe it briefly at the end. It's greedy method because the basic idea is that if you remember the brute force approach, where you're going to try everything, the idea is that instead of trying everything, you're going to be a bit more greedy. So you're going to try some, then try to add some more. But instead of everything, you just go incremental. So you start from 1, then you get 2, then you get 3, and you don't always explore everything, okay? The other approach is what is called the convex relaxation approach. The convex relaxation approach is basically saying, well, instead of looking at the 0 norm, let's replace, which is just counting how many coefficients are different from 0. Let's actually replace this with the L1 norm, which is instead of counting, okay, so if you put here an indicator that says whenever the coefficient is positive, I count 1, this is just the 0 norm. If instead of the absolute value, okay, you put the, if you think of the absolute value as some kind of soft thresholding, okay? You just take, if it's 0 is 0, otherwise it takes the absolute value. The other thing you could do is that you take a hard thresholding like that basically says if the coefficient is positive, I count 1. Then if you sum up, you get exactly the 0 norm. So you can view this as a relaxation of this, when instead of an indicator, you just take the absolute value. So each coefficient doesn't count 1, but count how big it is. Okay? So now this is just the absolute value. So the absolute value looks like this. Okay? So our concern was computational, because the problem was not convex. How about now? So we have the square loss, okay, for the time being, and the square loss is smooth and differentiable and convex, okay? And smooth and differentiable is in the same thing twice. What about the L1 norm?
Mostly differentiable.
It's mostly differentiable. Well, that mostly is not going to be good enough. We're going to have to use our little convex analysis ideas. But the problem with the other one was not only differentiability, but it was worse than that. The L0 norm not only is not differentiable, but it is not even convex, okay? Whereas this guy is going to be convex. So tomorrow, so suppose that we want to discuss the computational perspective, okay? If you remember when we did SVM, we already encountered a situation where the functional was convex but not differentiable. Do you remember how we tried to solve it? Well, we didn't try, we actually gave an algorithm. Subgradient, okay? We defined what's the subgradient and we did subgradient descent. Okay? You could do that here. You could just go in and we're gonna do something similar. Take the gradient of this, take the subgradient of this, which is not gonna be hard, right? Because as he noticed, this is just something which is almost differentiable, so it's gonna be almost always 1, and then it's going to be just a bit annoying in the middle. So you can just try to go there, write down. It's going to be a super simple expression, and you just go in and run your iteration. Okay? So the whole day of tomorrow will be dedicated to convince ourselves that in the case where you don't have a generic convex functional, but you have this kind of special functional, which is a sum of 2 terms, where the first term is not only convex, but is actually differentiable with a nice gradient, and the second term is convex. So one of the two, they're both convex, but the first one is actually also differentiable. Then you can do something better than subgradient methods, okay? You can exploit the specific form of this functional to get a class of algorithm, which is what is called is based on the idea of so-called forward-backward splitting and proximal operators idea, okay? Which gives you a very general framework to solve problems that essentially look like the sum of 2 terms, where one of the 2 terms is convex and the other one is convex differentiable, okay? And you will see this will generalize to many, many, many class of methods beyond L1, okay? So this is why we're going to spend the whole hour tomorrow kind of optimization techniques. Similarly to what I told you, when we discussed subgradient methods for SVM. The reason why these methods became so important lately is because they define very simple iterations. Okay? Unlike second-order methods or more refined optimization techniques, the cost of each individual iteration is relatively low. And so you can implement this even if the problem is huge. Okay? So that's why we're sticking to this class of methods, which were and still are state-of-the-art. So what we want to try to do in the last 10 minutes is try to get a feeling of why this makes a huge difference with respect to considering just the squared norm. Okay? So here, notice that this one here is just a special case of that, okay? It's just a special case where we consider as the dictionary the singular value of the matrix. It's easy to see. And in this case, we could confuse ourselves by just computing the solution explicitly. This was sparse. We're going to do that too, okay? But now we're going to take a slightly more geometric perspective to try to convince ourselves that this L1 norm does give you some form of sparse solution, okay? Notice that for now, we don't have any reason to believe that this convex relaxation should be much better than this one. They're both convex relaxation, but we have no particular reason to believe that this one is going to be better than that. Correct? So we're going to try to convince ourselves that that's indeed the case. You know what? This is actually a tricky step, and I start to be tired, and I imagine you're too. So let's do something a bit lighter and conclude a little bit earlier. And then tomorrow we're going to start with this so that we don't burn ourselves completely out. So tomorrow we're going to see exactly, we're going to start by checking why this L1 should give us a sparse solution, why L2 doesn't. Okay? Let's finish instead with like a couple of more qualitative questions. Okay? And the question is, why sparsity could be a good idea? Okay? Let's discuss 1 second. We discuss, okay, fine, it might be that it's a right prior, but what you might hope to get out of it, okay? For which reason it could be important?
We can drop a lot of our sum terms. Right?
You can drop a lot of time, and why is that good?
Reduces competition.
So one reason is because the idea here is that you have this, okay, or you have this huge matrix, okay? You have a matrix that looks a bit like this, okay? Or actually might look big in every possible dimension. And by doing sparsity, you can drop columns. So computationally, this sounds like a good idea. Fair enough. What else? Well, memory computations, yes. So in a broad sense, I don't know which one he meant, but both, right? Time and space. Good. Absolutely. What else?
Produces more simple interpretable models.
Right. That's a word I really love. Interpretability. Okay. If you do something like, yes, you are in some sense sparse and something is big, and it's the principal components. Okay? As long as you believe principal components carry good information, in some sense here you're going in and looking which principal components are useful to have good prediction. Fair enough. But if these dictionary elements are something that actually matters to you, suppose the case of genes, okay? Suppose that you're taking measurements and you know which measurements you have to do. Suppose you have to design a test for somebody. You have 10 tests and you want to know which one is more predictive. You don't want to have a combination of these tests. You're going to be annoying if you have to follow 10 of them, okay? You want to do 1 or 2. So what you want to do is to select which one. So in many biological applications, these kind of techniques are really the state of the art, because besides providing you a solution, they also give you a story that says, you know what, if you take these measurements 1 to p, then what really you should look at are these few measurements that are selected by my procedure. If you think of a case of the genes, that's a typical case. You have a disease, you want to predict. In many, many situations, you're not going to use this as the ultimate answer. So you have data, you want to try to predict, you want to try to understand the disease, okay, and you want to predict if it's going to be an aggressive or not disease. But oftentimes, you don't believe that this is the last. Oftentimes, the number of data points you have is not significant enough to believe them completely. But so the doctors oftentimes what they want to know is which genes are important, because then I can go in, do some other measurements, cross this information with other information I have and try to get a better picture of how the disease works. Okay? So you use here the tool as a lens to look at the data and get some information that will allow you to get a better understanding, which is what is often done with machine learning, especially applied to natural sciences, where you use machine learning as tools, okay, to look at the data and get the indirect measurements. So interpretability is one of the key. What else? The list in my brain I have 3. So you actually said 2. Well, one way to think about it is that it's good to go back to this. Take a second of the sizes of this problem. Okay, we have n points. You have d. That's it, because the other one you can recover. Okay, you have n samples and d variables. Okay, and you want to try to solve that. So statistics 101 tells you that how big should be n if you want to try to solve that problem. Think of it as a statistical problem. You have a certain number of unknowns. Now you have some number of measurements. You want to solve the problem. How many are the unknowns in that problem? No, just 1 second. No, don't ruin my last 5 minutes. Yes. If you have d, you really need n order of d. But if now the last row tells us actually you have sparsity, delete everything but the first 2 columns, that the one that matters, you need n order what? Well, let's say that the sparsity level is s. Okay? Then that will be the dream, right? That's kind of the case where, as somebody was saying, you can go in and do some kind of filter of just those components. You pick them and you keep them out. So from a statistical point of view, when d is much larger than n, which is what we call the high dimensional statistics scenario, so when n is much smaller than d, there is no hope you can get a solution to this problem. Okay? We already had our least square problem, which kind of bet that in some sense you're sparse on the principal components. But this one is actually saying that if you're sparse on something else, maybe you have hope to be able to solve the problem in a good way with n much smaller than d. Okay? So from a pure statistical point of view, if you want the number of effective degrees of freedom of the problem is not d, but it's just s. So the problem looks like this. Okay? There is a very wide matrix because it has few rows and many columns. And then you have a very long vector w, and then you produce a vector y, which is short. Okay? If the true vector, so the data are generated by a vector, maybe you add some noise, and then you want to go back and find the vector that generated them. If the vector is really full, well, there's no free lunch. But suppose that I tell you that my vector has only a few components different from 0. Then in some sense, find them. Because if you could find them, then you just need much less data to solve the problem. Okay? So, in fact, one thing we're not going to discuss, but has been the main theoretical contribution in this field, is essentially showing that this is too good to be true. You have to pay something. Okay? But the good news is that typically you pay something which I might not write in the latest day, but it's something of this order. Okay? And if you want to ignore this for a minute, this is a bit worse than what you can prove. But it's basically saying a total dimension, but just logarithmically. So even if D is huge, you pay a logarithm with that. But linearly, you only pay the sparsity level. Okay? And as I said, it's actually a little better than that. And this thing has a whole connection with sampling theorems, where basically you have the idea, in sampling theory, you have this idea that you look at the maximum frequency and you have to go twice that maximum frequency. And this says, well, but what if, sure, the last frequency is here, but everything else is empty. You just have a couple of frequency. Can you do something better than getting all those samples? There is a whole connection with that field that I just mentioned, but we don't have time to go into. Okay? And so these are the three things that I thought might be worth, before we actually delve more into the modeling and computational aspect of this method. These are three motivations. Okay? We start just by doing formal analogies we would have done so far, and here we discover a few things which are at least three reasons why looking at sparsity could be interesting. Are computational, the hope of setting both in time and space, trying to get interpretable model that go beyond pure prediction. Notice that here we're basically looking at the W themselves rather than just the prediction that W's allow. And finally, high-dimensional statistics. The hope that if a model is sparse, this could be another way to get a meaningful solution, even in the situation where we have few points and a lot of dimensions. Okay? And notice that here dimension could be either the raw dimension of the data, but it can also be that I chose, because I want a rich model, many, many, many features. Okay? So I choose a dictionary which is very, very, very large. So I could have a situation like the genes where I have 10 patients and I take the gene expression, which are order of tens of thousands of measurements. But I could also have images that are 100 by 100, but now I actually by hand extract features because I want them to have a rich description of the image. And maybe I can take 2 million features out of a 100 by 100 image. Okay? So that's another case where P is huge. Okay, well, that's unbounded. You can take as many as you want. Okay. So this is good enough. So tomorrow we combine and look at the modeling and computational aspects of this.